So for this second lecture, we're going to mainly talk about mirror descent. So title is Mirror Descent and online decision making. I'm writing online decision making rather than online learning or Bandit because we will see that it's useful more generally than just for what we did this morning, and I will touch on that. So there are links with online algorithms. So first, let me remind you the frameworks that we're working in, and so let's say 0, reminder. So we're going to talk about online linear optimization. So this morning we talked about Bandit linear optimization at the end, but now we're going to focus on online linear optimization. So the setting is like this. So K is going to be a convex body in Rn. So this is a convex body. Okay, so it's a convex set with non-empty interior and compact. And the game goes like this. So at each time, t, from 1 to capital T, the player picks xt in k, and the adversary plays a linear function. Adversary picks lt, which is in it's in the polar body, so really it's in Rn, such that lt.x is smaller than 1 for any x in k. Okay, so what we were doing this morning, k was just the simplex. We were picking a probability distribution, playing from this probability distribution at random, and our loss was indeed the inner product between our probability distribution and what we observed. We also talked about the case where you have many points embedded in n space. So then you can imagine that the convex body that you're playing on is the convex hull of those points. And when you play a point inside, playing a point inside is like playing a probability distribution over the vertices. So we will see that in more detail in lecture 3, but this is the setting in which we're going to work today. And the regret, right, is just the sum of lt dot xt minus x for t equals 1 to capital T, and it's the maximum of this over x in k. Okay, so you pick the best point for your for the data, and you compare yourself to this. Okay, so now what I want to talk about, a big thing that we did is that in the information theoretic framework, we related our regret to the movement in the probability distribution, to the movement in the posterior, right? And we wanted to show that this posterior distribution cannot move too much because it's decreasing its entropy. Now what I want to argue is that there is another point of view on this, which is the stability. So now I want to use this stability as an algorithmic guiding principle. Okay, so stability as an algorithm design principle. Right, the point of the lecture now is to come up with algorithm in a principled way. So stability as an algorithm design principle. Okay, so you remember the key point was to look at the L1 norm of xt minus xt plus 1. So now what we want to do, I'm just going to enforce this as follows. So let's say we have the sum for t equals 1 to capital T of lt dot xt minus x. Okay. Then I can just introduce, the term xt plus 1. So before we had that in expectation, x, which was x star, was equal to xt plus 1. But now I can just introduce this term. So I get lt dot xt minus xt plus 1 plus xt plus 1 minus x. And now this term, it looks like what we had before. Okay. And so this term, I will be able to bound it by the movement. And this term, I will interpret it as a one look ahead term. So let me make this precise. So now this is bounded by two terms. I get the sum for t equals 1 to capital T of the norm of xt minus xt plus 1 in some norm. So let's say this is assuming the dual norm of LT in some dual norm is bounded by 1. So this discussion is more general than playing on the simplex, but to apply it on the simplex, just think that this norm is the L1 norm and the dual norm is the L infinity norm. So you get this term for Hölder's inequality applied to this, plus the sum for t equals 1 to capital T of LT dot xt plus 1 minus x. Okay, so how to interpret this? So this is exactly what we had to deal with this morning. Okay, now we just forced it into our equation, and this I will think as a movement cost. So we see from this term that we want our next choice xt plus 1 to be not too far from xt. This term, I will think of it as a one look ahead regret. What does it mean? It means here, you see in this equation, xt plus 1 can depend on LT. Okay? So now I get to see the loss, and upon seeing the loss, I can make my decision. So in this term, I want to pick xt plus 1 to minimize LT. So what does the algorithm has to do? The algorithm has to trade off between not playing too far from the previous point and also trying to minimize the loss function that it's seeing. Okay, in the one look ahead term. Yeah?
When we compare this to what we had this morning,
yes?
there seems to be a small difference because this morning we were comparing ourselves to the best I,
Yes?
one of the best summits,
Yes?
but not the best probability. Like, here we had, before we had some summits and we
Yes?
were playing inside the convex L, which were the
Yes?
simplex.
Yes?
But we are not comparing ourselves to the best simplex, but to the best summit. However, here we are comparing ourselves to the best point in the L.
Yeah, but you know, because this is a linear function, yeah, the minimizer is going to be on the boundary. It's going to be at one of the vertices. Yeah, but good point. Yeah. So the big difference with this morning is this one look ahead term. You know, in this morning we just had the movement cost, but it was for a very particular. You know, these guys were doomed martingales of the optimum. Now we're in the worst case situation. Right now, I'm going to tell you an algorithm, and now we see that to design an algorithm, we have to trade off between those two things. Okay, so we want to be stable yet to minimize the loss function. Okay, yes.
The norm has to be chosen in such a way as to explain the geometry of T again.
Yes,
because,
yes.
for example, the L1 norm is special for the simplex.
Yes, exactly. So yeah, so I won't talk too much about this in this chapter, but in the next chapter we will talk about this. But right, think of this. You know, it's just more general than what we did. But think of K as either a Euclidean ball, and then you're working with the L2 norm, or the simplex, and then you're working with the L1 norm. Okay. Okay. So when you understand this, then I think a reasonable strategy is gradient descent. Okay. So let's talk about gradient descent. So gradient descent, as all of you know, it's the most basic algorithm to minimize a function. You know, you're at a point, and you just take a little step in the direction of the negative gradient. Okay, so the gradient is the direction where it's going up the most. The negative gradient is the direction where it's going down the most. So you take a little step in this direction. Why does it make sense in this case? Well, because you know, if you take a little step, you're not moving too far away. Yet you're trying to minimize the loss function. So whose function are we taking the gradient of? Well, of the linear function LT. Okay? So gradient descent would be like this. Xt plus 1 is equal to xt minus eta LT. Right? This is the gradient of the linear function LT dot. So this makes a lot of sense to try to think about this. Now, I want to argue that it doesn't make so much sense in general, especially when you think, you know, in these terms of non-Euclidean norm and L1 norm and things like that. You could imagine that you're in infinite dimension, and then this is an element of your primal space, of your Banach space B. And this guy, really, it's a linear function. It's an element of the dual space. It's an element of B star. Right? So you're adding an element of B and an element of B star. This doesn't smell very good. And indeed, this is not appropriate when you will work with the L1 norm. So let me put it slightly differently. This equation, you can also see it, so it's equivalent to saying that xt plus 1 is the argmin over x in Rn of your function that you're trying to minimize, lt.x, plus a term that tells you that you shouldn't move too far away, 1 over 2 eta, the Euclidean norm between xt and x squared. Okay, it's easy to see that if you look at the first order optimality condition of this function, you just take its gradient. What is the gradient? It's Lt plus, okay, the 1 over 2 cancel with this guy, plus 1 over eta times xt minus x. So when this is equal to 0, you find that xt plus 1 is indeed xt minus eta Lt. Okay, so those two things are the same. And now you see in this formulation, even if you don't like to talk about infinite dimensional spaces, in this formulation, it's very clear that here, your notion of movement is Euclidean. It's the Euclidean distance. But remember, we want to talk maybe about online learning on a finite action space. Then the norms, the appropriate norm, we're moving on the simplex. We're moving probability distribution. So we want to move with the L1 norm. And we see that gradient descent is not going to cut it, because gradient descent is tied to the Euclidean geometry. Okay? So what mirror descent will do is that in this formulation, it's going to replace this Euclidean norm by some notion of distance which is more appropriate to the L1 geometry. In this formulation, which is my favorite way of thinking about it, is that instead of adding a dual point to a primal point, it's first going to map the primal point to the dual, then take a gradient step in the dual, and then come back to the primal. Okay? Yet another viewpoint is as regularization. Okay, so here, this is going to be like the stability. This is just type checking. I don't know how to call it. Just doesn't type check. And the last one will be the regularization. And all of those point of view are really the same thing. It's just different names. And again, it has been invented infinite number of times. So the last way to view this set of equations is as the argmin over x in Rn. Let's say you start at x 1 equals 0. So this is the argmin of the sum for s equals 1 to little t of ls dot x plus 1 over 2 eta, the Euclidean norm of x squared. Okay, so what is this saying? This, if I just were to minimize this, this is playing the best point given the information that I have right now. So given all the losses that I have seen right now, this would be, if I really wanted to exploit and say, okay, what point do I believe to be the best? It's the one that minimizes the sum of the loss against x. It's my current optimal point. Of course, my current optimal point could be very far, it could be very different from the true optimal point. Maybe the information that I have right now is not representative of what's going to happen in the future. So what I do is that I don't want to play this point because it could be very unstable. Think in dimension 1. I keep seeing functions like this, linear functions that oscillates like that. Then I keep changing my mind. Is this the best point or is this the best point? I keep shifting all the time. Okay? And every time I shift, actually I'm making a huge mistake because I saw that slope. I place this guy, but in fact, the slope on the next round is this one. Okay? So I keep following the best would be a terrible idea. And indeed, if you were just playing this argmin, your regret would be, you don't have a non-trivial regret. You have a regret linear in T. So what you do is that you add regularization. Okay? You try to, so this is a basic idea in machine learning in general. To avoid overfitting, to avoid believing too much in the current data, you want to choose something which, okay, fits pretty well, but also is simple in some way. And here a good notion of, the notion of simplicity here is a Euclidean norm simplicity, is to have a short vector. Okay? And again, you see that this notion of regularization does not seem very appropriate on the simplex. Something which seems more appropriate is maybe to say, okay, I want to fit well, but I still want to have a high entropy. Okay? I want to hedge, so I don't want to be too focused. Okay? To avoid being too picky, being picky means having a small entropy. So I want to trade off being fitting the data and having a high entropy. So in this formulation, a natural thing to do is going to be to replace the Euclidean norm by the negative entropy, because I want to minimize. Okay, and that's, when you do that, you will exactly get multiplicative weights. So that's what we're going to see. Okay, so again, the mirror descent is going to be either you replace this by some general function phi, a convex function phi, or here you get a notion of distance which is induced by phi, which is going to be the Bregman divergence, or here you map from the primal to the dual using the gradient of this function. So now I will explain things in terms of this. So mirror descent. And mirror descent was first formulated by Nemirovsky, and it was written in a book, okay, what am I doing? Nemirovsky and Yudin. And the year is something like 83 for, I think, the translated version. Okay, so the idea goes like this. So so we have this potential phi. So this potential phi is going to be our notion of regularization. It's going to be the thing that induces the notion of metric. It's also going to be the map from the primal to the dual using the gradient. So phi is going to be from some set D that contains K to R, and phi is convex. Now, associated to phi, let me define the Bregman divergence between x and y. This is the error that you make when you do a first-order Taylor approximation of the value of phi at x using the information at y. So it's phi of x minus phi of y minus grad phi of y dot x minus y. Okay, this will be important in a minute. Okay, good. Now, what is the algorithm? The algorithm goes like this. Here is a picture. So we have K here. So this is K. And, this is D. So this is the set on which my convex function is defined. So think, if you want something concrete in mind, K is a simplex and D is a positive orthant. Okay? And think of phi being the negative entropy. If you take phi to be the negative entropy, then the Bregman is going to be the relative entropy. We will do these calculations. So I think of this as my primal space. Now, I have a point xt right now, and I want to do a gradient step. So the first thing that I'm going to do, so that I add, a dual point to a dual point, is that I'm going to map to the dual space. And my map from primal to dual is going to be using the gradient of this function. I find this to be a very natural way to do it, but I'm not saying at all that this is the only way to do it. Okay? You could have a more complicated map than the gradient of a fixed function. I don't know if this is useful, but I'm just pointing it out. So you use this gradient. Now you're at grad phi of xt. This is your dual point. Now on this dual point, you take a gradient step. You end up at grad phi of xt minus eta lt. Okay, this is your new point after the gradient step. Now you want to map back to the primal to get back a primal point. At the end, you need to give me a primal point. So the inverse, so the convex function, its gradient, it has an inverse map, which is the gradient of the Fenchel dual. So I will remind you this. So this is the gradient of the Fenchel dual. So recall, the Fenchel dual is defined like this. The Fenchel dual, phi star, at a dual point theta. This is the supremum over all x in your primal space of the inner product theta dot x minus phi of x. Okay, so what's the way to think about this object? It's a very, very natural object. So you know that the convex function, you can always define it as the supremum of linear functions. Okay, so what is a linear function? Well, it's just a function like this. It's theta dot x plus some constant, plus some offset. The definition of the Fenchel dual is exactly this offset, this constant that you need to add, so that you can represent your function phi as the supremum of linear function. Okay, so under very mild assumption, which we are always going to be verified for us, phi of x is the supremum over theta in Rn of theta dot x minus phi star of theta. So again, the differential dual is defined so that your convex function, you view it as a supremum of linear function, and it's just the function that you need to add. It's the intercept at 0 of those linear functions. Okay, that's all it is. Okay, and here I'm using notation where these are extended value functions. I can take value plus infinity if you're outside of the domain of definition. And the key point, I will leave this as an exercise. You can just check the first order optimality condition, and you will see that grad phi star at grad phi of x. So let's say claim, and I will leave it as an exercise, very easy to check. If you apply grad phi star at grad phi, you find x. Okay, so these things are inverse to each other. So grad phi star is indeed the map to move back to the primal. Okay, so now you move back to the primal, and you're at this point. Grad phi star of grad phi of xt minus eta lt. But you have a problem. You have one problem left to deal with, which is an important one, is that you might be outside of your set of constraints. Okay? As we'll see when you will run this with the entropy, basically what the entropy will do is that it will change addition into multiplication, because the gradient of the entropy is a log. So it really maps addition to multiplication. So addition in the dual is going to be multiplication in the primal. Now when you will just multiply, you will move outside of the simplex. You will not be normalized to have some of the entries to be 1. So you need to project back. Of course, you're not going to project in Euclidean norm. I mean, the whole point of this discussion is to move away from the Euclidean norm. And a natural, maybe it's not obvious, it is not obvious at first sight, but a natural way to project is going to be using the Bregman divergence. And we'll see very soon why it's natural. So what you do is now you project. Okay, so this is the argmin in the Bregman divergence between x, and let's call this point zt plus 1. It's the argmin between zt plus 1 and x, okay, over x in k. Okay, so the algorithm, you can write it in one formula. Xt plus 1 is equal to the argmin over x in k of the Bregman divergence between x and grad phi star applied to grad phi of xt minus eta lt. How many parentheses? And of course, naturally, if you were to take phi to be the Euclidean norm squared, let's say a half, so let's do one example for now. If I take phi of x to be 1/2 of the Euclidean norm squared, then grad phi of x is just x. So this map between primal and dual is just the identity map. Okay? But maybe this doesn't make sense on my space, and I want to do something else. So the other thing we're going to do is the entropy. But there are many, many other things that you can do, and we'll talk about them, some of them today. Now, you see, I won't talk about these two other viewpoints, but really these two other viewpoints are also valid. So I define mirror descent using this first equation, but you can define it using the regularization. It's called then follow the regularized leader, and it's just you change this by 1/2 eta phi of x. Similarly here, instead of the Euclidean distance, you can put the Bregman divergence, and this will give you the same algorithm. Okay, is there a question on the definition of the algorithm? Yes.
The second calculation is interesting because basically the proximal operator of this linear form defined by the laws.
Yes.
So I was wondering if you generalize with using some other stuff which is non-linear but has a nice prox.
Yes.
Would become some sort of a projected.
Yes. So people do that a lot in convex optimization. In our setting, it won't be relevant But for pure convex optimization, yes, this is an idea that makes a lot of sense. Yeah. You have the same question. Okay, anything else? Yes?
I just want to say about the projection with the Goldman layer. How do you do if the algorithm is not K? Because here you constrain over X in K, and
yes.
we just want to avoid any projection, classical projection.
Yes.
If your algorithm is outside K?
No. So I do project. The only question is, in what metric do I project? So I do project. What I don't want to avoid projection. I want to avoid projection in Euclidean distance. But it is a projection. It is a projection. Okay, so good. So now we're going to do, so we have two terms to analyze. We have the movement and the one look ahead term. Okay. So what I'm going to do right now is show to you that the beauty of mirror descent is that the one look ahead term is always automatically bounded for any phi. So there is just zero assumptions that you need to make about phi to bound this term. This will be for free. Notice that this is not a crazy property. I mean, I could just move to the minimum of LT. If I move to the minimum of LT, then of course this is always going to be negative. So just the mere fact that the one look at regret is bounded doesn't tell you anything. But for mirror descent, we can also hope to bound the movement cost if you select the right regularization. Okay, so I will do now the analysis in two steps. The first one is very general. It says that for any phi, this term is controlled. And the second one will be, okay, let's say we are on the simplex with the L1 norm. What do we pick for phi? What is a good regularization? And then we will see multiplicative weights come out. Okay, so now we will do the analysis of the one look ahead term. Okay. And four. And the goal of this paragraph is to give you intuition. Okay, some of the calculations that I do here were already done by Nemirovsky and Yudin in their book in '83. It's just the interpretation that I'm putting on the equation is new. It's not theirs. And I find it much easier to work in continuous time rather than discrete time. So we will do the discrete time proof. It's going to be airtight. But let's do for intuition the continuous time version. So what is the continuous time version? So for intuition, we consider a continuous time setting. So now the adversary, instead of choosing a loss function at every time step, it chooses a path of loss function. So LT is going to be, so now I put T in parentheses to make it clear that we're in continuous time. T now is in R plus. Right? And LT is a vector in Rn. So we have this continuous path of loss function. And what we can do, because we are in this one look ahead term right now, okay, so xt plus 1 is chosen as a function of xt, we will assume that we can react instantaneously. Okay, so xt defined using, let's say, ls for s smaller or equal than t. Okay, so we can use everything up to the current time step. So just to clarify a little bit, we have the discrete time setting. And we have the continuous time one. So in discrete time, we saw that we had two terms. We had this term, the sum of LT dot xt plus 1 minus xt. In continuous time, minus x, sorry. Oh, and maybe, sorry, let me call this y rather than x. So we will think of opt as y. I just use a different letter to make it clear that it's not related to the algorithm. So this is y. So we have this term, which is the one look ahead regret. In continuous time, it's just going to be the integral of the inner product between LT and x of t minus x dt. Okay? You can just imagine that any discrete loss is given, for a unit time step as a continuous loss. Okay, so the loss, just think that this loss, it's piecewise, constant. So on every window of size 1, it's constant. Okay, so this is like an extreme one look ahead. It's like continuous look ahead. Okay, good. So in fact, it's formal. You can really, if you can control this, you can control this. And now the movement was the sum of the norm. And now in continuous time, it's just going to be the integral of the norm of the derivative, x prime of t dt. Okay, so these are the two things that we want to control now in continuous time. Okay, so if you remember the analysis of multiplicative weights, it was a potential-based argument, and we said, okay, let's look at the L1 norm of the weights, and this was a bit magical. Now, the whole point of mirror descent is that it comes equipped naturally with a potential. There is a natural potential, which is this Bregman divergence. Okay, so let me do that. So, potential is going to be the Bregman divergence between y and our current point. So the way we're going to measure our distance to opt, so this is opt, this is the optimal point that we want to get to at the end, is using the Bregman distance to opt. Okay? So what is this? Again, this is phi of y minus phi of xt minus grad phi of xt dot y minus xt. And what I'm going to show to you is that we can easily take the time derivative of this. And we'll see something very nice happening. But I forgot to say something else before, which is I want to derive what is the continuous time version of mirror descent. Okay, so first, continuous time mirror descent. And what we're going to see is nice, hopefully. Okay, so to derive continuous time mirror descent, let's assume that I rescale my step size by some epsilon. And this, instead of defining xt plus 1, is defining x at time t plus epsilon. So what I'm saying is x at time t plus epsilon, this is equal to the argmin over x in k of the Bregman divergence between x and grad phi star of grad phi at time t minus epsilon eta L of t. Okay, so this is a step of size epsilon, and now I'm going to take epsilon go to 0 and find the time derivative of x of t. Okay, so I will describe to you an evolution using a differential equation. But first, let me let me remind you of first-order optimality condition for constrained optimization. Okay, so you all know first-order optimality condition for optimization of a convex function is just that the gradient should be 0. Now, if you have a constraint, it should be that the gradient is in a certain set. So reminder, if you have a convex set like this, then there is this notion of a normal cone. So the normal cone of k at a point x, okay, let's say this is x. This is a very, very natural quantity. It's a set of directions, it's a set of vectors, theta, in Rn, which are negatively correlated with any direction going inside, such that for all y in k, if I do theta dot y minus x, this is negative. Okay? So again, it's just a set of directions which are negatively correlated with anything going inside. You know, if this is my normal here, this is my normal here, then this part of the body is defined by the set of points whose inner product with this and that is negative. So in particular, if I look at this cone, you know, anything in this cone is negatively correlated with anything going inside. Okay? Because you see, I can take any positive combination of this direction and that direction, and this gives me something negatively correlated going inside. Okay? So this is the definition of the normal cone. Why is this important? Well, it's important because of the following fact. So let's say x star is the argmin of f of x over x in k. This is equivalent, so let's say f is a convex function. This is equivalent to minus grad f at x star is in the normal cone at x star. Right? Let's see one direction. I mean, both directions are the same, but let's say it in words in one direction. Let's say this was not true. Okay? So if minus grad f is not in the normal cone, then there is a direction going inside which is positively correlated with the negative gradient. Meaning that if I do a little step in this direction, I reduce my function value. So x star could not be the optimum. Okay? So this is the thing. Now, another name for this is that, you know, I can write, so this is equivalent to saying, grad f of x star plus lambda is equal to 0, with lambda is in the normal cone. So this is the Lagrange multiplier version of this. Okay, so lambda is the element of the dual cone such that this is 0 is a Lagrange multiplier. Okay? And it has certain property in terms of the constraints which are tight at this point, etc. This you can all see it from the picture. Now, why did I tell you this? I told you this because we want to see, you know, what is this point, the minimizer of this, but we're doing constraint minimization. Now, what is the function to which we're going to apply this lemma? It's this function. So I need to take the gradient of this. Notice that, just note that the gradient with respect to x of the Bregman divergence between x and y, remember it's this phi of x minus phi of y minus grad phi of x, blah, blah, blah. It's just a difference of gradient. It's just grad phi of x minus grad phi of y. Okay, so the gradient with respect to the first argument of the Bregman divergence is the difference of gradient. Good. So now with those two elements, I can write out what this is. So this is equivalent. So I need to say that the gradient of this plus a Lagrange multiplier is equal to 0. What is the gradient of this? So the gradient with respect to x of this is equal to grad phi of x minus what? Minus the gradient of this thing. But grad phi star is the inverse map of the gradient. So grad phi of this is just what is inside. So this is minus grad phi of x of t plus epsilon eta lt. Okay? So I get that this thing tells me that grad phi at x t plus epsilon minus grad phi at x at time t plus epsilon eta lt. This is in minus the normal cone at x t plus epsilon. Okay, this doesn't look so great, but you see that when I normalize by 1 over epsilon and I take the limit as epsilon goes to 0, I have something really nice. Okay, maybe, yeah. So this implies, and it's a squiggly imply because it's not really formal, so take 1 over epsilon and take the limit when epsilon goes to 0. You see what I have here, this first term is going to be the Hessian of phi applied to the time derivative. So this implies that the Hessian phi at xt times x prime t plus eta lt. This is in minus nk at x of t. Okay, so it's not really a differential equation, but it's a differential inclusion. Okay. And more than that, okay, so really the equation, so the definition, if you want, so the definition of continuous time mirror descent is that x prime of t, the Hessian phi at xt, x prime of t should be equal to minus eta lt plus lambda t, with lambda t in the normal cone. And we also want x of t to remain in the convex body K. Okay, so the first equation, this is called the differential inclusion because it tells you that it has to be in some set. And when you add this constraint, it tells you that it's a viability problem. So not only do I give you, a set of valid velocities at every time, I also tell you where you have to stay. And so Nemirovsky and Yudin, they really didn't really do this equation. They just did the derivative of the potential, which I'm going to do soon. And in particular, they weren't really interested in the continuous time version because what they really cared about was the real, algorithm. But I also care about information theoretic method. So the continuous time version makes sense to me. But then you have to prove that this exists, that this is well defined, and maybe it's also unique. So one theorem that we proved. So this is myself with Michael Cohen, James Lee, Yintat Lee, and Alexander Madry. And I will mention what this paper is doing towards the end. But in particular, we had to use this equation, and what we showed is that there is existence and uniqueness up to mild assumption on phi and LT. So existence and uniqueness okay, whatever. If, let's say, L is continuous, Hessian phi is continuous, and also phi is strongly convex. Okay, strongly convex just means that the smallest eigenvalue of the Hessian is bounded away from 0. Okay, maybe just a word about uniqueness because it might be surprising. I'm giving you a set of velocities rather than a unique velocity. The point is, it's really like this. So when do the velocities matter? They matter when you're on the boundary. Okay. Now, when you're on the boundary, two things can happen. Either you're staying on the boundary or you're going inside. If you're going inside, then it doesn't matter the force that you apply. So when I say the force that you apply, I mean the Lagrange multiplier. Maybe you put a big Lagrange multiplier, but it doesn't matter because the second you're inside, these guys disappear. So those multipliers are not continuous. Okay, those guys are discontinuous. Now, so what I just said is that if you're going inside at the next instant, it doesn't matter what force you apply. If you stay on the boundaries, then it turns out that there is a unique choice, provided that you're moving. If you're not moving, there could be multiple choice. So basically, there are three options. Either you're not moving, there are multiple choice, but you're not moving. You're moving on the boundaries, and then there is a unique choice. Or you're moving inside, and then it doesn't matter because the second you move inside, the force disappears. This is also closely related to the scorecard problem, which is related to other things. Okay. It doesn't matter for us. But, okay, so now I want to do the potential-based analysis. Now that I have a formula for my time derivative. So what I'm going to do now is that I'm going to take the time derivative of the potential, and you will see that we will connect back to the key intuition that I was giving you, during the very first lecture on multiplicative weights. So what is the derivative with respect to time of d phi y x of t? This is really the most important calculation. So let's see. So y is not moving. So this is 0. Now here, what term do I pick up? I pick minus grad phi of x of t dot x prime of t. When I take the derivative with respect to this term, you know, it's a product. I have to take the derivative with respect to the first term, and then, you know, another term is taking the derivative with respect to the second term. Let me start with the derivative with the second term. So I get minus grad phi of xt dot, and here what do I get? I get minus x prime of t. And here we're already very happy. Okay, this is crucial, is that you have a cancellation. Okay, the derivative of this term cancels with the derivative when I take the derivative with respect to this term. So what I'm left with is only the derivative with respect to this term. And what is the derivative with respect to this term? It's minus the Hessian phi at xt applied to x prime t, inner product with y minus xt. Okay, so I said these two terms, they cancel. So I'm left with only this. And now you see the whole point of mirror descent. It is defined so that I know what is the value of this guy. Okay, what is the value of this guy? Well, it's minus eta lt plus lambda of t. So what is this? This is equal to eta lt plus lambda t inner product with y minus xt. But now here is the next beauty, is that lambda t is in the normal cone. So lambda t is negatively correlated with any direction going inside. But y minus xt is the direction going inside. So lambda t dot y minus xt is just negative. So this is smaller than eta lt dot y minus xt. Okay. And now it's great, because now we can explain in English what's happening. So what is happening? What is this term? So lt dot y is what opt is paying right now. Lt dot xt is what I'm paying right now. If I'm paying more than opt, if lt dot xt is much bigger than lt dot y, if I'm feeling some regret right now, then my distance to opt is decreasing. So whenever I regret the action that I'm taking, I'm learning about opt. I'm getting closer to opt. This is exactly the same intuition as what we were saying about multiplicative weights. When you decrease, you know, the weight of everybody that mispredicted, if opt did predict correctly, then you just didn't decrease opt and you decreased everything else, so you got closer. And the right notion of getting closer is this Bregman divergence. And here you see these equations are completely general. This is true for any phi. Okay. Also, why is this inequality? Why do we expect this inequality? Okay, it's very nice. It's a normal cone, etc. But it's just saying that, you know, with this mirror descent business, you were outside of the convex body, and now you project. You better have the properties that when you project, you notice that opt is in the set of constraints. So you want that this projection only helps you. Okay, it cannot hurt you. It only helps you. And mathematically, this is witnessed by the fact that lambda is in the normal cone. Okay, so let me write this as a lemma. So now you see, this is really a potential-based argument. What we're saying is that our regret is controlled by this derivative of a potential. So when I integrate over time, I get the following lemma. So let me write it here. So this implies the following lemma. If I look at the integral of L of t dot x of t minus y, this is upper bounded by what? Okay, so I just put this on the other side. Okay, so when I integrate over time, when I integrate the time derivative, I get the value at the end minus the value at the beginning. Okay, but the value at the end is just a positive term. The Bregman is always positive because phi is convex. So I just get minus the value at the beginning, which I put on the other side, and what I get is the Bregman between y and x naught, x at time 0, over eta. Okay, so this is true for any phi. Just mirror descent satisfies that this one look ahead regret. okay, when you react instantaneously to the losses that you see, is bounded by the distance that you had at the beginning over eta. And recall the multiplicative weight bound, which was that the regret is bounded by log n over eta plus eta times L star t. That's the very first bound that we proved. This log n over eta is exactly this term. Okay? This Bregman divergence, you will see that it's just essentially the entropy, the negative entropy of your starting point, which is going to be log n. So we'll do this calculation. So we already explained, now we explain this log n over eta term is just the one look ahead regret of mirror descent with the entropy. Now we want to understand this term, and this term will come from the movement, okay, which we haven't done yet. Okay, I will give you a second to think about this while I look at what I want to say next. Yeah. Yes, please.
So here we got the theoretical bound for any phi, right?
Yes.
Any phi that verifies with my conditions.
Yes.
So it applies to phi to define the classical radial descent, right?
Yes. Yes.
So okay. So like,
Yes.
Like, this doesn't necessarily showcase the interest of the mirror descent.
No, not at all. Yes. So the interest of mirror descent is really, I mean, the interest of mirror descent is first of all that this is true for any phi. Yeah. This is great. But then, yes, the design of the right regularization will come in the movement analysis. The movement is the thing that depends on the geometry of your space, whether it's L1 or L2. Or, so it makes sense that it's the movement term that you know.
Yeah, and so here.
Yeah.
So I get why we, in that case,
yes.
We don't want the Euclidean geometry, we want the entropy because we want the edges. Right?
Yeah.
What in general, because in general, what determines what's the geometry?
Yes, yes. I mean, this is there is no in general. And I will mention an open problem in an hour or so, which is my favorite open problem. And it's really after this, after trying to say for general metric, what is the right notion of entropy? And this analysis leads you naturally to this question, and I don't have an answer, and I don't think anyone has an answer. And yeah, it's a great open problem, and there is a concrete bound to improve, so we will go after this. And also I can say, next lecture, we're going to work a lot with designing this regularization term in terms of what is called a self-concordant barrier. So this is another geometric notion of a convex body, and we'll see that it's very natural for what we have to do. But yes, there is no general answer.
So even though we don't know the exact mapping between the geometry and
yeah.
Like what is the mathematical object that has an impact on the potential you choose? K?
Yes, it's in what we're talking about right now. It's the norm. It's really the norm that you put. It's K with its norm.
Okay, and this norm we put it on the loss.
This norm we put it on the movement. So I didn't erase it. This is this norm.
Okay,
the norm that measures the movement.
This movement it was part of the inequality, right?
Yes.
So it was a majoration.
Yes. Yes. Yes.
And so was it like I don't quite remember in the original loss?
It's not necessarily tight. Is that your question?
Yeah, because like the original loss did not have this norm.
Yes.
So we choose this norm in the majoration, right?
Yes, yes, yes. But then yes, absolutely. But then I'm going to tell you another problem, which is called metrical task system, where this norm comes as part of the problem.
Okay.
And then, you know, then it's more natural. It's just there, you know. Here it's like a clever thing to introduce it, but in this other problem, it's just given to you, and then you have to work with it. Yeah.
So, like, I mean, in general, without any
yes.
information, what it means is that the relevant potential
yes.
depends on the way we did the first majoration, right?
Yes, yes, absolutely. Yeah, yes, exactly. But there are still many papers to be written, you know, about with clever choice of phi.
Sure.
So I'm going to show you a few ones today, but there are more. There is more that you can do. Okay, so now what we just saw, we had two terms to bound, right? This one look ahead term and this movement. So now we have to talk about the movement. How do you bound the movement? Sorry. I will just keep this. So movement analysis. And here, as I was saying, I don't have anything general to tell you. We have to look at a special case. So movement analysis for K equals the simplex and the norm equals the L1 norm. Okay, so now let's see, what do I want to say? Okay, so this is the term that we have to bound. And again, I reminded you the multiplicative weight bound that you have log n over eta plus eta L star t. What is L star t? L star t is the integral of Lt dot y. So the hope, just taking inspiration from this, but you can have other motivation to look for such an inequality, which I will mention later. The hope is, could we say that the norm of x prime t, the L1 norm, is bounded by Lt dot y times eta. So if we could prove such a bound, then when we integrate, we get that the movement cost is bounded by eta times L star, and we would exactly recover the multiplicative weights bound. Okay, but the difficulty is that we don't know what is this y. So a weaker inequality would relate this left-hand side, which depends on the algorithm, to something that only depends on the algorithm. And what is this? Well, we know by this bound that Lt dot xt is a lower bound on Lt dot y up to an additive term. So can we, a weaker bound, or a stronger, it's a stronger bound, sorry. A stronger bound would be that x prime t, L1 norm, is bounded by eta Lt dot xt. If we have this, then using the lemma, we get this up to some additive term, and then we recover the multiplicative weights bound. Yeah?
That is, most of the inequalities could be pretty much generalized by, for example, the cone is basically the sub-differential of the indicator of K.
Yes.
So if you replace I subscript K by some convex function, then you would have an analog of all these results, including the mirror distance algorithm.
Yes, that's correct. You can do that. And this is related to what you were also asking before with the proximal term. So basically, essentially what you're saying is that you don't have to linearize everything. And some part, if it's simple, you can keep it non-linearized. Yes. And again, this is valid and interesting for optimization, for offline optimization. Okay, so let's see this. Okay, so what is this? Again, this is just the norm of the Hessian phi at xt inverse applied to eta Lt plus lambda of t L1 norm. Okay, so we want this inequality. It looks complicated, but now we have to work. This came for free, but now we have to think about what would be a good phi so that this is true. So let's take a leap of faith and first ignore the Lagrange multiplier and see what we get. That's the first leap of faith. The second one is, let's say, inverting this Hessian, it sounds complicated. Let's try to look for something simple a priori, which is a separable regularizer, meaning that phi of x is the sum of phi of xi. Okay, so simplification. These are simplifications you make to search for a good phi. Ignore lambda and assume that capital phi of x, this complicated multidimensional function, is just a sum of one-dimensional function, phi of xi. Just something simple, something separable. Then what happens? Okay, so the L1 norm of the Hessian phi at xt inverse. So first of all, the eta they cancel, so we don't have to care about eta. Now you get this, the L1 norm of this. What is the Hessian? The Hessian is just a matrix whose diagonal is phi double prime xi. So the inverse is 1 over phi double prime. So this term is equal, It's the L1 norm. It's the sum for I equals 1 to n of Lit over phi double prime of xi. Right? This is just an identity. And we wish this was smaller than the sum for I equals 1 to n of Lit xit. Okay? And we have flexibility to find phi. So now I claim that this equality is just true if you take phi of x to be x log x. So phi of x equals x log x. This means that phi double prime, so phi prime up to a constant, it's log x. So phi double prime, it's 1 over x. So 1 over phi double prime at x, it's x. But if you take little phi of x to be x log x, then capital phi is nothing but the negative entropy. Okay, so we find that you want to take phi of x to be the sum for I equals 1 to n of xi log xi. And the reason why this entropy came naturally is just because we had the control on this one look ahead regret. Then we wanted to control the movement. And we said, okay, let's control the movement by the one look ahead regret, which is the thing that we have a hold on. And by doing this, we find naturally the entropy. Okay, so let's write so now that we have a regularizer, we can write what is the dynamics. Okay, what is actually happening. And we'll see that what's happening is just a continuous time version of multiplicative weights. Okay, so now I claim that the dynamics are given like this. So x prime at location I, so the time derivative at location I, what is it? So I have to apply the Hessian inverse to eta times the loss plus the Lagrange multiplier. What is the Lagrange multiplier? I'm on the simplex, right? So on the simplex, there is only one constraint, which is that the sum of the xi should be 1. The constraint that it's non-negative is not acting because this thing blows up, the derivative blows up when you get to 0. So there is no constraint at 0. There is only a constraint that the sum has to be 1. If you write what is a normal cone, the normal cone is just, spanned, it's just the line spanned by the all 1 vectors. Okay, so the Lagrange multiplier is just a multiple of the all 1 vectors, which means that this Lagrange multiplier is just a constant applied to every time derivative. So the formula that you get is that this is equal to xit. This is the inverse Hessian times eta lit plus some mu. And what is mu? Mu is the Lagrange multiplier such that the time derivative, the sum of the derivative is 0. Okay, mu is such that the sum of the x prime it is equal to 0. And there should be a minus. So you see, I'm just decreasing at a rate which is proportional to how much loss I'm suffering right now, which is exactly the same thing as what we're doing in multiplicative weights, just a continuous time version. Okay, so this is a continuous time multiplicative weights. Okay, so this is, you can make all of this formal, while staying in the continuous time, but I find it also somewhat instructive to do the discrete time analysis. So let's do the discrete time analysis and just see how to translate all those continuous time things into the discrete time. Okay, so 6, discrete time analysis. Oh, and maybe one thing I can say is you can see in particular with this dynamics that really the Lagrange multiplier does not induce more movement. Because what is this guy doing? Well, all of those terms are negative. So it means that this term, to enforce that the sum is 0, it should be negative. This guy should be negative because there is a minus sign. So I can just look at the positive part. I can just look, at the negative part of the movement, right? Because I get this, of course, the norm of x prime, the L1 norm. This is bounded by 2 times the L1 norm of the negative part. So up to a factor of 2, I can just focus on the negative part. And in the negative part, I can ignore the Lagrange multiplier. Because the Lagrange multiplier, really, the way to think about it is that you have those actions, and you have a loss that's coming at you. So the loss is telling you, okay, guys, you should decrease, your probability mass. And what the Lagrange multiplier is saying, okay, yes, you have decreased your mass, but now it has to be redistributed so that the sum is 1. You're not allowed to just decrease the mass. You should remain a probability distribution. So these guys, they decrease at various rates, depending on what is the loss. And then the Lagrange multiplier, what it does is that it redistributes the mass everywhere. Okay. So let's do the discrete time analysis now. And this will be particularly important for the Bandit setting. Okay. So what's happening? Well, what's happening is that I have an error term. Okay. This is what we did was just the first order part. Now there will be a second order part. Okay. Second order part is going to be some eta squared. And the eta squared will come from the second derivative of this thing. So let's first see what we should expect. So we expect an additive error of something like the second order derivative of the Bregman divergence in our potential analysis. Okay, so what is this? So we saw that the first order derivative is this thing. The only inequality was when you applied the Lagrange multiplier. So let's ignore the Lagrange multiplier and let's just look at this. Okay, so let's just look at this thing and let's say this is equal to the time derivative. So then we want to say that this is roughly up to lambda, which we will see how to deal with. It's up to lambda, it's the time derivative of eta LT dot y minus xt. Okay. Now, let's assume that we are at a time where the loss is not changing. So again, you remember I told you that intuitively you can think that the continuous time loss is just a piecewise constant loss. So then if you do that, then this, the time derivative of this is 0, so I'm left with the time derivative of this. So what I get is that this should be equal to eta LT dot x prime t with a minus sign. Okay, let me just continue here. Okay. Now, what is x prime t? X prime t, okay, maybe I just erased it. Again, if we ignore the Lagrange multiplier, it's just the inversion applied to eta LT. By the way, what I'm doing right now is like the second most important calculation of this afternoon. The most important one was this. This is actually the second most important. This is what will enable Bandit, the Bandit to work. Okay, so what is x prime t? It's minus the inversion applied to LT. So what I find is this is equal, ignoring the lambda, to eta squared LT dot Hn phi at xt inverse applied to LT. Okay, and now let me introduce a notation in terms of local norms. So the local norm of H at x, this is the norm induced by the Hn at phi. So the Hn phi at x applied to HH and square root of that. Okay, so just view this as a bilinear form, this Hn, it's a matrix, applied to HH and take the square root of this. This is the local norm at x. So the way to think about it is that the potential phi, it transformed my nice convex body in Rn into a Riemannian manifold, where at every point I have a tangent space, which is just all of Rn, and the inner product on this tangent space is given by the Hessian at this point. And in fact, this manifold, when you will have a barrier function which blows up, it's a hyperbolic manifold, and we'll see that this is important tomorrow morning. Okay, and this is crucial for Bandit. But right now, we just have this definition of norm. So the dual norm, just by definition, the dual norm is the norm with the inverse Hessian. So it's square root of the Hessian phi at x inverse applied to HH. So what do we see? We see that we get this is equal to eta squared, the local norm of LT, the dual norm squared. Okay? Makes sense that it's a dual norm. This is a dual object, right? So we apply a dual norm to it. So we expect that the mirror descent analysis that we did in continuous time, in discrete time, is going to work the same up to this additional term. And the fact that we have a local norm here instead of just a basic Euclidean norm is going to be crucial for bandits. And we will see this hopefully today, just for the multi-arm bandit. So the multi-arm bandit is just what I told you this morning when you have a finite action set. And the arms, again, they correspond to actions. Okay, so let me state the theorem. And then prove it. So we expect this, but of course there could be a third order derivative. I mean, really, this is going to be true only if we can stop our Taylor expansion at the second order term. So we will need to say that the third order term does not matter too much. What does it mean that the third order term does not matter too much? If you look at this equation, it means that really the Hessian of phi does not change too much on the scale of a step. So on the scale of the step, you want to say that the Hessian remains roughly constant. And this well-conditioning condition is exactly going to lead us to self-concordant barriers. Okay, this will be for tomorrow morning, but for now, it's going to be just an assumption. So here is the theorem which will say all of those things. So the theorem is like this. So assume that phi is well conditioned in the sense that you have the following implication. So if you look at the point, let's call it yt. Let's call it zt plus 1. Let's call it yt. So such that, okay. So if you have a point which is like this. Okay, so now we are in discrete time. So we were at xt, we do a gradient step, and I want to say, what do I want to say? That's not what I want to say. I want to say that this point is in the segment like this. So you have a point which is on the dual segment. Okay, so this is a segment in the dual, and you want to say, it corresponds to some curve in the primal, and you want to say that for any point which is like this, something happens. So you want to say that this implies that the Hessian phi at yt is not too different from xt in the sense that in the positive semi-definite sense, this is bigger than 1 over some constant c times the Hessian phi at xt. Okay, we'll see that very soon. So let's assume that our function phi is not too crazy, meaning, again, that on the scale of a mirror step, the Hessian does not change too much. Then what? Then you get that you regret. So the sum for t equals 1 to capital T of Lt dot xt minus x, This is going to be bounded by the Bregman divergence between y and x at time 1 over eta plus 2 eta over c times the sum of those dual norms. Sum for t equals 1 to capital T of the norm of LT norm at xt dual squared. So this is the theorem. This is a very important theorem that you can use to prove many things. So really, there are two terms. There is a term which depends on the size of your set, and there is a term that depends on the variance of your losses. Why am I talking about variance right now? So this is the magnitude of your losses, but thinking ahead of Bandit, in Bandit you won't observe LT. So what we're going to do is that we're going to build an estimator of LT. So LT is going to, instead of LT, we will have L tilde T. So L tilde T is going to be a random variable which estimates LT. And now the key point is that we will have to estimate the variance of those estimators in the local norm. And this will be key, because those variants will blow up in certain conditions. So let's do the proof of this theorem. Very likely that I will mess up somewhere, but let's try to do it. Okay, so to not mess up, we have to use a continuous time calculation to inspire us. So let's see. So we have this guy. We said that this was equal to this was upper bounded by this. Okay, good. So what we want to relate is, did I write x? Yeah, I wanted to write y here. Right? Y is up. So what we want, the first thing we want is we want the sum for t equals 1 to capital T. Okay, maybe without the sum, we just want LT dot xt minus y. It would be nice, if really this continuous time perspective was right, meaning that this thing is upper bounded by the drop in one step of this. So is this bounded by d phi of y xt minus d phi of y xt plus 1? Okay, this is the kind of thing that I would like to be true, if the continuous time analysis was true. But I know I will pay another term, plus a term which is going to be roughly something like the norm of LT. So it's going to be the norm of eta LT at xt dual squared. Okay, so this is the kind of thing that I would like to prove. If I prove this, then okay, then I'm done. Because when I sum, I will get a telescopic sum. And here I will get just the sum of the variance term. So that's what I'm hoping to prove. So let's see what we can get. So what is LT? So now we are in the discrete time setting. So we know that grad phi of zt plus 1 is equal to grad phi of xt minus eta LT. And then xt plus 1 is just the projection. It's the argmin of d phi of xt of xzt plus 1 over x in k. Okay, this is the algorithm that we're looking at. So let's just write LT in terms of the grad phi. Okay, so what is this? So this is grad phi of xt. And let's put a eta just to simplify. So this is grad phi of xt minus grad phi of zt plus 1 inner product with xt minus y. What do I know about, so eventually I want to bring in xt plus 1. What do I know about xt plus 1 with respect to zt plus 1? Well, I know this. I know that it's equal to the projection. So what does it mean that it's equal to the projection? Remember, it means that the gradient of this is in the normal cone. The gradient of the Bregman, remember that it's the gradient of phi, it's the difference of the gradient of phi between the two arguments. So this tells me that the gradient of phi at xt plus 1 minus the gradient of phi at zt plus 1 plus a Lagrange multiplier lambda t plus 1, this is equal to 0. Okay? And this guy is in the normal cone of k at xt plus 1. This is what I know. Okay, so what it means is that if I take the inner product of this with, say, xt plus 1 minus y, I will find something positive. So let's bring in xt plus 1 minus y when I test against grad phi of zt plus 1. Okay, so I don't know if it's useful for you to have different colors, but it's useful for me. So we have different terms. We have grad phi of xt dot xt minus y. And then we have this term minus grad phi of zt plus 1. And I just said that for this one, it seems to make sense to introduce minus xt plus 1 plus xt plus 1, because that's what we know how to control. So we get minus grad phi of zt plus 1 dot xt minus xt plus 1. By the way, what I'm telling you right now is the way it's proven everywhere, okay? Which, okay, we can use the continuous time intuition to guide us, but if you don't have the continuous time intuition, it seems very, just algebraic manipulations, at least to me. But I think with the continuous time, we see a little bit more what's going on. But still, this is the way it's proven. Okay, so minus grad phi of zt plus 1 xt minus xt plus 1 minus grad phi of zt plus 1 dot xt plus 1 minus y. Now, we did this exactly so that we can see this term. So this term, again, what do we know about it? We know that when I take the inner product of lambda t plus 1 with xt plus 1 minus y, what do I find? I find something negative. Yeah, but this is, okay, good. So we know that this minus this is equal to minus this minus lambda t plus 1. So when I take minus lambda t plus 1 dot this, I find something positive. So what I find is that this term is bigger than minus grad phi of xt plus 1 dot xt plus 1 minus y. Okay. And here, right at this point, we have essentially used everything we know about the algorithm. So now we have to do some manipulation to find those Bregman appearing. Okay, but essentially in terms of inequalities, we're basically done. Maybe we can use the convexity of phi, but that's all you're allowed to do at this point. So let's see if we can conclude. And spoiler, we will be able to conclude. Okay, but let's see what do we want. Okay, so what is this term? What is this term? Okay, so if I expand in terms of what is the definition of the Bregman, you see that phi of y cancels. And what I'm left with is phi of xt minus phi of xt plus phi of xt plus 1 minus grad phi of xt dot y minus xt and plus grad phi of xt plus 1 dot y minus xt plus 1. Okay, so now let's do some pattern matching. So let's see. We do have this term, yes, very good. This term is equal to that term. Now, what else? This term, I think we have it. Yes, we have it. It's this term. Okay? So we have this term is equal to this term, and this term is equal to that term. So in the end, what we just proved, okay, so what we have, so far, what we formally proved is that eta lt dot xt minus y is upper bounded by, okay, so we have those two terms, which is basically this Bregman, this difference of Bregman. So y dot xt minus d phi of y xt plus 1. But what we forgot are those terms, so we have to subtract them. Minus phi of xt minus phi of xt plus 1. And what I forgot is this term. Minus grad phi of zt plus 1 dot xt minus xt plus 1. Okay. And what I want to make appear now, the question is, the only thing that I have to work with is this thing. And the question is, can I, out of this, make appear something which looks like this dual norm? So instead of this dual norm, I'm going to make appear something else, which is the following. So the norm of LT squared at xt dual. This is in fact roughly like the Bregman divergence of the Fenchel dual between grad phi of zt plus 1 and grad phi of xt. So why is that? So you see, this Bregman divergence, really the way you can think about it is that it's very similar to the local norm, except that I'm not sure at which point I take it. You know, when I do a second order Taylor expansion, I find that the Bregman is equal to the local norm, but we're not sure at which point it is. So here I'm just ignoring that. Now, the difference between grad phi zt plus 1 and grad phi xt is exactly eta lt. So I can make this guess. Now, here is something nice. The Bregman divergence in the dual is very closely related to the Bregman divergence in the primal, in the sense that this is equal, so this I will leave you as an exercise. This is a Bregman between xt and zt plus 1. Okay? This is the Bregman between xt and zt plus 1. So by definition, it's nothing but phi of xt minus phi of zt plus 1 minus grad phi of zt plus 1 dot xt minus zt plus 1. By the way, just an aside, this is the most the proof with the most algebraic manipulations that I will do over all the lectures. I mean, all the other one will be more intuitive. I mean, again, this is intuitive, but just you have to sit down to really follow it, I think. Or maybe many of you follow, I don't know. So this is the Bregman between those 2 points is equal to this, and we want to relate it to that. So we're pretty close, okay? But we see that, for instance, we have phi of xt plus 1 instead of phi of zt plus 1. And I said one last thing that you are allowed to use that we haven't used yet, really, is the convexity of phi. So if you just use the convexity of phi, and I will not do it, but it's immediate, you get that this term, this blue term, is exactly upper bounded by the Bregman between xt and zt plus 1. Okay, so we get, this is a true inequality, so let me write it, just this final inequality. So what we show is eta lt dot xt minus y is upper bounded by the difference, by the drop in Bregman plus the Bregman between xt and zt plus 1. Okay, this is just true. Okay, you can ignore everything else and just try to prove this, and this is just true. Now, the only last step to do in the proof is to use this well conditioning to replace this last Bregman term by a local norm. And this I will not do it, but it's simple. The reason is again that this Bregman by a Taylor extension, this is equal to the Hessian at a point between xt and zt plus 1. And what you want to say is exactly that the Hessian at a point between xt and zt plus 1, it's exactly a point yt like this. And the Hessian at this point is not too far from the Hessian of xt. Oh, and that should probably be a c then, instead of 1 over c. And then you prove this. Okay. Yeah.
If phi is strongly convex,
Yes.
then phi star is Lipschitz.
Yes.
Can you use this? And then you've shown that this local norm is approximately given by this.
Yes. Yes.
So you have that. You have the norm which is
Yes.
Lipschitz locally. Can you use this?
Yeah. So if phi is strongly convex in some norm, then in fact the local norm becomes basically this norm. Yeah, you can do that. Okay, so now we will do a 5-minute break, and I promise after that it will be less technical. So what we're going to do is that we're going to use this theorem to do the Bandit version, to give you an actual algorithm for Bandit information. Okay, so let's meet again at 3:40. All right, so let's start just quickly by revisiting multiplicative weights with this mirror descent point of view. So this is 7, if this is true. So revisiting multiplicative weights with mirror descent. And the bound that we'll get is just a tiny bit different than what we had before, and that will be useful for Bandit. So, okay, let's just do the calculation. So we take phi of x, which is a sum of xi log xi. So, and let me put a minus xi. Doesn't matter a linear term because it's all in the curvature, but just simplifies. It allows me to drop some constant. So the gradient of phi is just log xi. And the Hessian of phi is just diagonal with 1 over xi. Okay, so when I do a step in the dual, if I'm at grad phi of x minus eta lt, what is this? So this is just saying, so let's call it zt plus 1. Okay. This is the same thing as saying that, grad phi of zt plus 1. This is the same thing as saying that the log of this is equal to the log of xt minus eta. So it's the same thing as saying zt plus 1 I, or zi t plus 1. This is equal to xit times e to the minus eta lit. So you see, this is exactly the way we were updating the weights in multiplicative weights. So the way we were updating the weights with multiplicative weights was by multiply by 1 minus eta lit. And now instead of 1 minus eta lit, we just find an exponential function. Okay, this is roughly like 1 minus eta lit up to a second order term. Okay, so we see that this is indeed, this corresponds exactly to the multiplicative weights. And now what is a normalization? I will let you do it at home. It's just an exercise. So the argmin of d phi between x and z over x in the simplex, this is equivalent to x is equal to, or this is equal, the argmin is equal to z over the L1 norm of z. Okay, so if you have z with non-negative entries, projecting in the Bregman associated to the entropy is just normalization. Just write it down. You will see that by the first order optimality condition, it tells you that the difference of the gradient, so the difference of the log, is equal to a Lagrange multiplier, which is a constant in all entries because of this. So the difference of the log is log of the ratio. So you get that log of the ratio is a constant, so the ratio is a constant. And that's how you find this. So what we get is, so this implies that xit plus 1 is nothing but xit e to the minus eta lit normalized, okay, over the L1 norm of this. Okay, very good. What else do I want to say? Oh, yeah, what is the bound? So corollary of this theorem. And let me say something important now. So this sounds minor, but it will be important. So now it is important that LT, let's say LIT, is in 0, 1. And by 0, 1, what I mean is really that it's non-negative. Why is it important? Because if the losses are non-negative, then the well conditioning is going to be automatically verified. So let's see that. You see, this is the Hessian. Okay, the Hessian is 1 over xi. So when I take a segment in the dual, what I find is that I just multiply by e to the minus eta lit. But if lit is non-negative, then this is smaller than xit. I only decrease the coordinate. Okay, maybe lower or equal. I don't increase any coordinate. So if I decrease the coordinate, the Hessian just goes up. Okay, so this implies that the Hessian at this point is larger than the Hessian at that point because of this. So it implies well conditioning with c equals 1. So this implies well conditioning with c equals 1. Okay, and this is important. You can deal with negative entries, but then you need to do something different. Okay, so we get well conditioning with c equals 1, so we can apply this bound. So we get that the sum of LT dot xt minus y is upper bounded by the Bregman divergence between y and x1 over eta plus 2 eta. And now we have the dual norm of this thing. What is the dual norm? Well, the dual norm is the norm of the Hessian inverse. So the Hessian inverse is when I have xi. So the dual norm of h at x squared is just the sum of the xi hi squared. So you see the intuition of this is that it's a Euclidean geometry, but where I have, I mean, of course it's a Euclidean geometry, but what I mean is that you just have rescaled the axis. Okay? So what it means really is that for the coordinates where I have little mass, the norm is smaller. Okay, this is crucial. The norm, for the coordinates where I have little mass, I'm allowing a bigger magnitude. And this is going to be important in the Bandit case. So what you get is a sum for t equals 1 to capital T. Another way to write this is I will write it as x dot h squared. So plus the sum for t equals 1 of xt dot lt squared. And from this, it's an exercise to find again the bound that we did before, because this, you can bound it. This is bounded by LT, by the loss of your algorithm. Okay? xt dot lt squared, because LT is between 0 and 1, LT squared is smaller than LT. So the sum of xt dot lt squared is smaller than LT. So we get eta LT. So if you put it on the other side, you can just replace this eta LT by eta LT star. Okay? So this allows you to, so this recovers, this implies, the regret is bounded by log n up to a constant, log n over eta plus eta LT star. Okay, so we found back exactly the same bound as before. Again, the small difference, which is important, is that you don't find LT star on the right-hand side. You find LT, but it's okay because you can put LT on the other. You can put now this on the other side. You will just put a 1 minus eta in front of this, plus eta times LT star. Okay, so now finally, let's do an algorithm for Bandit after 5 hours of lecture. So propensity score estimate for Bandit feedback. Okay. So the basic problem is that we don't observe the full loss function. Okay, so we cannot run mirror descent. The idea is to estimate. So given LT of IT, with IT sampled from PT, we want to find an estimator. Find L till T in Rn such that we would like the expectation when you sample IT from PT of L till T to be equal to LT. So this is an unbiased estimator. Okay, and again, the picture you should have in mind is like this. Okay, you have these actions which are unrelated, and we have some crazy loss function over here. Now you're just seeing this value. You're just seeing this value. And I'm asking you to estimate the value at all the other points. I don't think you have so much choice. What you can do, and what we'll do right now, is just to estimate everything you have not seen to 0, and then appropriately renormalize the things that you have seen. So you have seen this. So what I'm going to estimate it is, I'm going to re-estimate it by 1 over the probability of playing it. So it's going to be just a point mass like this. So I'm going to estimate this complicated, possibly complicated function over this action space by just a point mass. And the whole point of tomorrow is going to do more refined estimators when you have structured over this set of actions. For instance, what if this set of points, they sit in n space, and I'm seeing a linear function? Then we will see that there is something much smarter to do than the point mass estimation. What if this function is a convex function? Then we will see that it's a delicate question, but you can do something. Okay? So that will be for tomorrow. So basically, the last topic we're touching on today is the thing that we're going to only talk about tomorrow. Okay? And we'll talk about this well-conditioning thing, which becomes more complicated also. Okay, so let's see. So what is the formula? The formula is just this. L till T, let's say at location I, is just what I said. So it's LT I, but I see LTI only if I is equal to IT. And I renormalize by the probability of seeing this. Okay, so this thing I can compute. It's 0 at every location that I didn't play, and at the location that I played, I put my loss and I renormalize it by the probability of playing. So the expectation of this is indeed LT. Okay, you see when I take the expectation, I sum over the probability that IT is equal to I, so it's the sum of PTI, and the PTIs they cancel, and I find LTI. Okay. So now what I want to run, I run mirror descent with L till T instead of LT. By the way, this goes back to a seminal paper by Auer, Cesabianchi, Freund, and Shapiri in 95. Of course, you know, yes, great, this is an unbiased estimator, but I mean, there is no miracle. This unbiased estimator has a very large variance. You see, if some action has a small probability of being played, then the variance is huge. Because the variance, the expectation of this squared, you know, it's going to be 1 over this probability. But now is the beauty. Now here comes in the local norm. The variance is 1 over the probability, but this 1 over probability is exactly going to be cancelled by the fact that the local norm in the entropic metric, they exactly discount the location with small probability mass. So the location with small probability mass, they count less. And they exactly count less by what I need so that the variance of this is going to be controlled. Okay, so there is, at this point, this is a little bit magic, and tomorrow we'll see that it's not magic, and there is something more general, which is called the entropic barrier, related to the log Laplace transform of convex bodies, and again, there is a principled way on, point of view on all of this. So let's do the calculation. So the theorem. So this algorithm is called EXP3, sorry. So this is called EXP3 for exploration and exploitation with exponential weights. And now I claim that exp3 verifies the following. My regret, so my expected regret, is going to be bounded. I get this term, log n over eta as before. And let's put a squiggly because I don't want to care about the constant. The constant are just 1 or 2, it doesn't matter. Plus eta nt. Okay, and notice that here I write nt and not lt or lt star. Okay, this is really going to be the time horizon, and we will mention this. Okay, so the proof. So the only non-trivial thing that we have to calculate is what is the expectation of the inner product between pt and lt squared. Right, this is this term. This term. I replace xt by pt because I prefer it when we play on the simplex, but okay. So this is pt dot lt squared. And of course it's a tilde, sorry. Okay, so what is this? So this is bounded by the expectation of the sum of pti. And then we have L tilde t squared. So LTI squared is just bounded by 1. So we get the indicator that I is equal to IT divided by PTI squared. Sum for I equals 1 to n. One of the PTI cancels with one of the PTI squared, and I'm left with, this is equal to the expectation of the sum for I equals 1 to n of the indicator that I is equal to IT renormalized by PTI. But what is this expectation? It's 0 with probability 1 minus PTI, and it's 1 with probability PTI. So in total, each term contributes 1, so I get that this is equal to n. So the local norm variance of this estimator is n. The variance, the naive variance is infinite. It's not controllable. But the local norm variance is controlled. Okay, so that's really the key. So mirror descent is useful for two different reasons in this context. One reason was that it automatically controls this one look ahead term. Okay, it's just automatic, and that if you pick a good phi, then the movement is also controlled. The other good thing is that the discrepancy between the continuous time and discrete time analysis involves those local norms, which are exactly what you need to control the variance with Bandit feedback. Okay, so really everything just falls in place. It's pretty miraculous. Okay, so if you optimize over this, you get square root n log n times t. Okay, so this goes back to 95, and those guys, they were just doing the proof that I showed you, in the first 10 minutes of multiplicative weight with this unbiased loss estimator. And if you do the proof a little bit more carefully, you find these local norms. You didn't need this whole mirror descent framework to do this. But now we will see that just an epsilon variation will do many good things for us. I will show to you now that you can remove this log n very easily, and that also you can get an easy data bound. Instead of t, you can get L star. And those were paper, some of them complicated, which becomes very, very simple with the mirror descent framework. And then after that, I will conclude with my favorite open problem that I promised. Okay, so what's the number? 8, 9. Okay, so more refined regularization. Let me just see, how do I motivate this? Yeah, I don't motivate it, okay. Okay, here is a leap of faith. So right now we add, so with phi equals neg entropy, we add that the inverse Hessian at x was this diagonal of xi. Okay, very good. Now, of course, if I add instead of power 1, if I had, I don't know, power 2 or power 3 or something, then I would just get something with a smaller variance. Okay, so I can change my function phi so as to improve the variance term. The trade-off is that as I improve the variance term, I will make the size of the set bigger. The question becomes, can you find a better trade-off between size of the set and variance than this trade-off, which is given by the entropy? So here we had a size of the set which was log n, and we had a variance which was n. But question, what about if I take, let's say, phi of x inverse is diagonal, let's say, of xi to the 1 plus epsilon? Just a little bit better. Let's see what happens. Okay. So what is this? What is the phi that gives you this? It's something like up to constant. I will not care about the constant again. Is minus the sum of xi to the 1 plus epsilon. And I probably messed that up. If I do 1 minus epsilon. Yeah, 1 minus epsilon, that makes more sense. Okay, so you see, let's say if epsilon is a half, then we get minus the sum of square root of xi. Okay, square root is concave, but minus this is convex. Okay, so instead of, this was the entropy. Now what we're taking is this thing, something like that. Okay, some other regularizer. It just seems to make sense from this point of view. So let's see what happens. So now what is the variance term? The variance term becomes the sum of, let's say, PTI to the 1 plus epsilon times the indicators that I is equal to IT over PTI squared. Okay, from I equals 1 to n, expectation. So again, one of the PTI is going to cancel with this one, and the other one is going to cancel with the expectation of this. So I'm left, instead of n, I'm left with the sum for I equals 1 to n of PTI to the epsilon. Okay? And now I can just apply Hölder's inequality. This is smaller than, I want to take the 1 over epsilon norm of this, meaning that I will take, I will take this to the power epsilon. So the other power on the sum of the 1 is going to be 1 minus epsilon. Okay, I don't know how you guys prefer to see Hölder, but in the end you get this. Okay, this is just bounded by n to the 1 minus epsilon. So you see, I didn't lie to you. We did improve a little bit. From n, we got n to the 1 minus epsilon. Now what about the size of the set? Okay, something I never told you is this. If you have d phi between y and x1, then if x1 is the minimizer of phi, then this is just equal to phi of y minus phi of x1, or it's upper bounded. That's if x1 is the argmin of phi of x over x in k. Which makes sense. Which starting point do you take? You just take the minimizer of your regularization over your set of constraints. Okay, so in this case, it's easy to see that the Bregman is just the difference of phi values. So this will be important. Please remember it. So what you care about is really the range of phi. Notice that this phi is always negative. So really, the only term that we have to care about is minus phi of x1. So what is minus phi of x1? Well, it's this sum, or minus phi of x. It's the sum of xi to the 1 minus epsilon for I equals 1 to n. But now again, I can just apply Hölder exactly the same way I did before, and what I will find is n to the epsilon. Okay, so the theorem is that if you do mirror descent with this functional, you get the bound which is n to the epsilon over eta plus eta n to the 1 minus epsilon t. So you see, it's pretty cool. When you optimize over eta, the n to the epsilon cancel, and you don't have any log n, and you get square root of nt, okay, which is bounded by square root of nt. And by the way, right now we are in this, I don't remember who was asking this question, but we are in this process of, finding via some art a good regularizer. Okay, I did try to motivate it a little bit, but the truth is that, you have to come up with it. I should say that people in the online learning literature, they tried to do things like this, but they didn't do it through the mirror descent framework, and they were just trying to do an L1 normalization. So you do a step using this, and then you do an L1 normalization. But this doesn't work because the L1 normalization is not the appropriate thing to do with this regularization. The projection in Bregman for this thing is different from an L1 normalization. Oh, I should say, this is Jean-Yves Audibert and myself in 2009. 2009 was a complicated proof, and okay, this is a simpler one. Okay, let me give you just another example. Easy data bound. So you see, the problem is right now our variance is just bounded by n. It doesn't take into account our own loss. Before, for just multiplicative weights with full information, we could, instead of nt, we had lt, our own loss. And this was good to find first order bound. So let's see how to get this. Well, here is an idea. Just take phi of x, which is minus the sum of log xi. Okay, this seems pretty crazy at first sight. It blows up to infinity, in particular when one of the coordinates goes to 0. So the range is a problem. But what is the local norm? So the Hessian phi of x inverse is now a diagonal with xi squared. Okay, I didn't say it, but these guys, when epsilon tends to 1, there is something that blows up. So when epsilon tends to 1, really you should take this thing, which is called the log barrier. And we will talk about it in a more general context tomorrow. This is the canonical example of a self-concordant barrier. So you see now the variance is xi squared. So what does it mean? It means that the term, the expectation of the local norm of L tilde squared at xt, let's say at pt dual, just the local norm cancels the 1 over pt squared. So really what you're left with is that this is equal to pt dot lt squared, which is bounded, so this is equal, just check it, it's equal, which is bounded by pt dot lt. So now with this barrier, the variance is actually your own loss, which will lead to an easy data bound. Of course, you need to care about the range, and for the range, you have to be a little bit subtle. You have to, not allow things to get too close to 0. I will not do it, but it's simple. And in the end, what you get is basically, let's say, they don't get closer to 0 than 1 over t. Then this could be as big as log t, but you have n terms. So what you get, really, theorem, is that the bound that you get is n log t over eta plus eta lt, which when you optimize, you will find square root of n log t lt star. Okay? I mean, the paper doing this before were not very difficult, but here it's really, really simple. Just playing with the local norms. Okay, is there any question on this before I move on to the last topic? Okay, so if not, I'm going to tell you now briefly about online algorithms. I said at the beginning that we would talk about mirror descent for online decision making, which is more general than just online learning. So let's talk about a topic that I really like, which is called metrical task systems. So this was invented in a different community. This is Borodin, Lineal, and Sachs. in 82. And their goal was to abstract and generalize a bunch of problems in online algorithms. And their model goes like this. So you observe LT, which goes from n to, let's say, R plus. So you observe a loss function on your set of actions. So the way to think about it is that this is a task coming at you. So now instead of actions, we're going to think of state. So this is a state space of size n, which we're going to endo with a metric. So think of a graph or something like that. So you have a state space, which is a metric space. And every time step, there is a task that comes at you. You have to complete this task. Right now, you are in a certain state. And upon observing this task, you get to move to a new state, complete the task in this new state, and then the next task comes. What do you pay? You pay the completion time in the state that you moved to, and you pay the movement cost. Okay, so update, so observe LT, update state IT in n to IT plus 1 in n. And what you, pay movement, which is some metric on this set. So it's the distance between IT and IT plus 1, plus the completion time LT in IT plus 1. So this is exactly like what we were doing before. This is exactly your one look ahead term, and this is your movement term. Okay, except that here it's all given as part of the problem. And the key difference in this setting, notice that here I have not assumed that the losses are bounded, because in this online algorithm problem, you might want to think of this task as hard constraint. You have to do something. For instance, maybe some state is just forbidden at this time step. You just cannot be in that state. You have to send the goods to some location, meaning that the loss could be infinite at some locations. If the loss is infinite, then you have to move, but also it means that it just doesn't make sense to compare yourself to a best fixed state. So what you want to compare yourself to is to actually a dynamic policy which is changing all the time. But then the regret notion is too strong. You cannot say, I'm going to do as well as the guy who is changing all the time and sees all the future, plus a little term. But you can say, I do as well as this up to a multiplicative term. So the objective now is the competitive ratio. And amazingly, mirror descent is again going to be just appropriate for competitive ratio. And for a third reason, I said at some point there was the most important calculation, then the second most important calculation, and now there is a third most important to control the competitive ratio, which maybe I will do. So competitive ratio, you look at the sum of those things, so the distance between IT and IT plus 1, plus LT of IT plus 1. And you normalize by the minimum of I1 star up to IT star of the same thing. Okay, so you compare yourself to opt. Very good. What do I want to say now? So, of course, we're going to be in a randomized setting. So we're going to play at random. So if IT is sampled from PT, then LT, the expectation of LT IT plus 1, this is just the inner product between PT plus 1 and LT, which is exactly our one look ahead term from before, one look ahead, which we know we can control with mirror descent. That's no problem. Now, what about the movement? Well, the expectation of the distance between IT and IT plus 1. Now, of course, you shouldn't take independent sample at time t and at time step t plus 1. But what you can do is you can couple them. So now there is a notion of coupling, but because I don't have much time, I just assume that you know those things, and otherwise you can ask me. This will not be anyway not be relevant for tomorrow. So you can couple, those two samples from time step t to time step t plus 1, and what you find is that this is equal to the Wasserstein distance between pt and pt plus 1. Okay, or the Earth mover distance. It's by definition the smallest distance between it and it plus 1 upon all joint variables, all joint couple it plus 1, such that it has distribution pt and it plus 1 has distribution pt plus 1. That's just the definition. And an example, just to clarify, is what happens when the distance is just uniformly 1. So just the trivial metric. Everything is just distance 1 of each other. Okay, there is no metric information. Then W1 is just the L1 norm. Okay, W1 between P and Q is just the L1 norm of P minus Q. Okay. So in this case, what do you find? You find that your movement is exactly the L1 distance between PT and PT plus 1, and you have a 1 look ahead term. So this looks like exactly what we were dealing with, when I opened this second lecture with the stability argument. But here it's like given, it's part of the problem. It's in the definition of the problem. Okay? Now, the problem is, so far, what we have done is that we were comparing to a fixed action. So now the question is, can we compare to a moving action? Okay. So the question is really, if you go back to the continuous time analysis and you run mirror descent to find those PT, the question is really, what is the time derivative of the Bregman divergence when y is moving? Okay, so assume that x is staying fixed for a minute. So we already did the calculation when x moves and y stays fixed. But now we have to understand what happens when y moves. So what happens when y moves? Well, remember d phi between y and x is phi of x minus phi of y minus grad phi of x dot y minus x. So when I move y, I just find grad phi of y times y prime. So I find minus grad phi. So I find, what am I doing? Yeah, I think that's correct. No, that's not correct. Yeah, thanks. I knew something was wrong. Doesn't matter, but so you find this at xt, and this dot y prime t. Okay? Okay. I mean, it makes sense. Now opt can move. So you do expect that the Bregman can now go up. It's not like you're just going to always zoom in on opt. Sometimes opt is going to take a decision which you don't understand. He's taking a decision because he sees into the future. You don't see, you're doing the best you can right now, and so the guy is moving away from you. But for him to move away from you, he has to pay. He has to move, I mean, by definition. And what do I mean exactly? Well, this is upper bounded by L times the norm of y prime t, where L is the Lipschitz constant. So, okay, this is the third most important calculation of the lecture. So this is upper bounded by L times the norm of y prime t, where L is, let's say, 2 times the supremum over x in the simplex of grad phi at x and the dual norm of this. So far phi, it was important because to control the movement, but now we see that we have a new condition in this framework that comes for phi. We want phi to be Lipschitz also. Okay? And phi to be Lipschitz with respect to a certain norm. And what is this norm? This norm is a norm that controls the movement. Meaning this, you can think of it as like a norm of pt minus pt plus 1. So when the metric is trivial, this norm is the L1 norm. But if the metric is more complicated, you get a more complicated norm. And now what you want, in addition for your mirror map phi, is that it's Lipschitz with respect to this norm. Now we have a problem. We showed that you can control the movement when you take phi to be the entropy. but the entropy is not Lipschitz. The entropy blows up towards 0. Okay, so let's see what happens. But apart from that, you know, if you put everything together, you can really see that you're gonna, your competitive ratio is exactly gonna be this Lipschitz constant. I won't do the proof, but that's, so let's make it as a, I don't know, a general theorem or something. So, general theorem. So this is myself, Michael Cohen, Yin Tat Lee, and James Lee. Should appear soon on arXiv. Is that the competitive ratio of mirror descent is bounded by L times the movement cost analysis. And this, for L1, we show that this was a constant. We showed constant. I won't explain more than that. So really, it's all about the Lipschitz constant. But right now, the Lipschitz constant could be big. Okay, so I wish I had time to explain this in more detail, but I don't want to hold you. Okay, so here is a theorem which goes back to Bourdin, Lignal, and Sachs in 82. Is that, what is it? It's that you can get a log n competitive ratio for D, which is uniformly 1. Okay, so the competitive ratio is log n when the metric is trivial. And the reason why, now it's, at least for me, it's perfectly clear now. The reason is because it all boils down to this Lipschitz constant. And if you do the calculation, what you will do basically is that you will chop off the small values. So instead of allowing everything to get to 0, you will allow it to get to delta, some small delta. And you will see that then there is a rounding procedure that you need. And the rounding will only work when delta is as small as 1 over n. So I will just write those things and you can ask me if you want. So stop if PTI gets below delta. This will imply L is like log 1 over delta. Okay, because you never get below a value of delta. And then rounding, by rounding I mean rounding from such a measure which has nothing below delta to something that can go to 0. Because you need, again, the loss could be infinite somewhere. So you need to be allowed to go to 0. So rounding only valid if delta is less than 1 over n, which gives you a log n. And now the big conjecture, my favorite conjecture, is that this is true for any metric. So intuitively, from an information theoretic perspective, the way I understand this is that, you know, the metric can only help you. It only gives you more information about how to move in this metric space. Now, once you say that, very naturally, what you might want to do is try to do the information theoretic argument that I did in the first lecture for this problem. The problem is that it fails. It just doesn't work. So there are many reasons why it doesn't work. One of them is that you don't have a Doob martingale. There is not a single, you know, point that you're zooming in. This guy opt, you see it's moving also. So now you will need to say the entropy, sometimes it drops, sometimes it goes up, which is exactly how the proof of the mirror descent goes. The proof of the mirror descent is exactly saying the entropy essentially decreases, except when opt moves, then it goes up. But I don't know how to do that in the information theoretic argument. And I believe if you could do it in the information theoretic argument, then maybe, hopefully, there would be a nice way to see that having a non-trivial metric just helps you. Okay, so this is open. What I can say, another thing that I like about this conjecture is that it really pushes you to think about a notion of entropy that matches a given metric. So entropy, just the usual entropy, is natural for the L1 metric. Now we found another notion of entropy, so a theorem, so this is BCLL18, is that for what is called for ultrametric, so for ultrametric spaces, conjecture is true. So what is an ultrametric? An ultrametric is just if you want, you have a tree. So your metric space, it corresponds to the leaf of a tree. And now the distance is just the shortest path distance in this tree. And in that context, the entropy that we're pushing forward is like this. You have your tree, and this is the space, the leaves. Now I want to see the tree as a filtration. I want to say that at any level, what I get is that I get a marginal distribution. So I can put myself at a different level of coarseness of this metric space. You know, if I look at it from the leaf, I look at it very, very precisely. But if I go up a little bit, I can look at the metric space from a coarser point of view. Now, if I have a probability distribution here, it gives me a probability distribution at any level. I can calculate the entropy at all of those levels. And what we do is that we do mirror descent with what we call the multiscale entropy, which is combining linearly all those entropies with weights which are given by the distance at which you're looking at the space. And if you do that, then and the space is ultrametric, then we can prove the conjecture. Question is, if you don't have this nice decomposition, then we don't know what to do. Let me just see if I can say something else. Yes, maybe just this notion of multiscale entropy. I think it makes sense in machine learning. You know, you have a set of images, and you know, maybe you have a distribution which is, I don't know, a car and a cat, or a distribution which is a dog and a cat. You know, this is distribution mu, and this is distribution mu. From a purely entropic perspective, you know, those two things have the same entropy. I mean, they are just, you know, probability of half something, probability of half something else. But clearly, I would say that this one is more chaotic, more random than that one. Why is that? It's because I think that car and cat are further away in some metric space. And the multiscale entropy will exactly do that. It will tell you that, yes, the multiscale entropy of this thing is much higher than that thing. Because this thing, as soon as I go up a little bit in the hierarchy, I see that those two things, they collapse, and there is no entropy left. So there is only entropy here at very fine scale. But at higher scale, there is no entropy, whereas this one, the entropy remains for a much longer time. Okay? Whether this is useful in machine learning, I don't know. Okay, I will stop here for today. Thanks.